Hello, madam.
Sir, audible, sir.
Okay, my voice is audible.
Yeah, sir.
At what time to start?
1:45, sir. We'll start, sir, with minutes. Participants are joining.
Okay, madam.
You can share the screen, sir.
Okay. Are you seeing my screen?
Yes, sir.
Hello.
Yes, sir.
Okay, madam.
Within 5 minutes, we'll start, sir.
Okay, madam. Ashwini, Amma, water na కొంచెం. నువ్వు బయట చేసుకుంటున్నావా?
Good afternoon, sir. Good afternoon, everyone. Good afternoon, everyone. All the participants. Welcome to the day 3 of FTP, 5-day FTP program. So it's my pleasure to introduce our esteemed resource person, Burli Tulasi Rao. Received his BTech degree in Electrical and Electronics Engineering from GMR Institute of Technology in 2012 and his MTech degree in Power Electronics and Electric Drives from NIT Surat in 2016. He completed his PhD in Power Electronics from the IIT Bhubaneswar in 2024. He is currently working as an assistant professor in the Department of Electrical Engineering at Anil Neerukonda Institute of Technology and Sciences, Bhiwanipatnam. His research interests include the applications of power electronics in renewable energy systems, DC to DC converters, and the reliability of power converters. Now, today's topic is coupled inductor based high voltage gain non-isolated DC to DC converter with quadratic input states for electric vehicles. Welcome, sir. Thank you, sir. Thank you for accepting the invitation. So now
Thank you.
I'm welcoming our resource person.
Okay,
Sir, you
madam.
can share
I'm
the
sharing.
screen.
Okay, madam. I'm sharing my screen now.
Okay, sir. Thank you.
Okay. Are you seeing my screen? Hello, madam.
Yes, sir. Yes, sir.
Okay. Can I continue now? Right now?
Yes, sir. Yes, sir. Yes, sir. You can continue.
Okay. Good afternoon, one and all. This is Burul Tulsirao. Okay, now I am presenting high gain coupled inductor based non isolated DC converter for electrical vehicle application. Today I am covering these are the topics. First, I will give the brief introduction of the basic structure of the electrical vehicle, and then how they are using the high gain DC converters in the electrical vehicle. Then I will discuss about the literature survey. In the literature survey, what are the possible high voltage gain DC converters and what are the aspects is there, and I will discuss in the literature survey. Then I will what are the objectives to achieving the high voltage gain DC converters. Then I will discuss the proposed concepts. Recently, these two papers are accepted in IEEE transactions. So one is in IEEE transaction circuits and system, and another topic is accepted in IEEE transaction power electronics. So these two proposed concepts I will discuss in the this FDP. Then after that I will discuss about the small signal modeling of the coupled inductor based high gain ZVS DC converter with leakage energy effect. So once we are designing the high gain DC converter, how can we verify the rise time and bandwidth and everything based upon our desired specifications? Once we will check the based upon the border plot, then the summary and references. Okay, first I will go about the introduction. In the introduction, I'm showing the typical structure of the fuel cell electrical vehicle. This is the basic structure. So in the generally nowadays using the two sources. I mean means two batteries are instead of okay, two batteries means one for high specific energy and another for high specific power. So high specific power battery means it instantly deliver the high amount of the power to the DC bus. Okay, here we can see the one is connected by using the bidirectional DC converter, another one is connected by using the high step up converter. Okay, one is the unidirectional flow and another one is for bidirectional flow. Nowadays they are using two batteries. Two batteries. One battery is designed for high specific energy and another battery is designed for high specific power. So instead of two batteries, the one is they are using the supercapacitor and one is for fuel cell. Okay, and one other way is for flywheels also they are using. It means this is the structure, but instead of the supercapacitor and fuel cell, they use the either by using the two batteries or one battery and one fuel cell, like that they are using. So here supercapacitor means this is the high specific power, means instantaneously deliver the power to the motor. Very large amount of the power instantaneously deliver or it will accept. So that's why it is using the for bidirectional power flow. So even though when the regenerative braking, when we are applying the braking means at the time this motor or whatever motor we are using in the fuel cell, that motor is act like a generator that will charging the supercapacitor. Okay, so this is the bidirectional power flow. So here the high gain bidirectional DC converter is required here. And another one, so from fuel cell. Fuel cell generally the voltage level range in 22 to 48 voltage range. In fuel cells means we'll discuss about the hydrogen fuel cell. And hydrogen fuel cell we're taking as the hydrogen as the fuel, and hydrogen react with the oxygen and it will raise the water and as well as the electrons. Well, a little amount of the power will it will generate fuel cell. So that power as the input to the this high step up DC converter. So means here the voltage level is very less, 22 to 48 voltage. But here our required voltage range in DC bus voltage 250 to 400. Means here we using the one inverter. After that nowadays they're using the motor, three phase motors they are using. So three phase motor when required the three phase supply. That's why once after this DC bus we are using the three phase inverter. The three phase inverter will give the three phase AC to the three phase motor. So for three phase inverter purpose, we require the 240 to 400 range of DC voltage is required. So what is the gain factor? Minimum, suppose if you take the fuel cell voltage is 22 to 250 voltage, almost the gain factor is required more than 10 times. Okay, here suppose we are taking the fuel cell is delivering the 48 volts. Here our DC bus voltage is almost 400 voltage. So within this the gain factor is required. Here the high gain step up converter must be capable of boost the voltage more than 10 times. Then only that converter is suitable for the this application. Similarly, this bidirectional DC converter also you should give the more than 10 times gain factor. Then only that type of converter only suitable for the specific applications. Okay, then why multiple times I'm talking about the high gain DC converter means, so what are the drawbacks in the conventional converter? Conventional converter means conventional boost converter, buck boost converter, CPIC converter, Zeta converter. So many converters is there in the conventional converter. These all the converters are suitable for the gain factor less than 5 times. So if the gain factor required, some applications is required, suppose 20 to 100 voltage, then we can easily go about the conventional boost converter. Then no need to go about the high gain DC converter. So if we are moving the gain factor more than 5 times, at the time the parasitic elements drop is increasing drastically. Why? Because whatever voltage we are achieving in the output side, same voltage stress is appears on the output side diode as well as the our MOSFET, whatever switch active switch we are using, the switch also. So the output voltage stresses, suppose if you are achieving the 100 volts output voltage here, the same 100 voltage stress is appearing on the diode, and that voltage stress is appears on the active switch also. So we are choosing the high rated MOSFETs and diodes. That if you are using the high rated switches means the internal on state conduction resistance also very high. So when the gain factor is increases more than 5 times, at the time the due to these parasitic elements effect and reverse recovery problem of the output side diode, so the efficiency drastically decreasing, sharply it is falling to zero. So due to ratio increasing the more than 0.8 times, after that that efficiency curve is drastically falling. So these converters are not suitable for the high gain applications. That's why we are moving into the new converters, new high gain DC converters. So this high gain DC converter not only using in the electrical vehicle, so many other applications also require this gain factor is required more than 10 times. Like that, the solar and fuel cells are generally non-conventional energy sources give the low DC output voltage, which requires the high gain DC converters to interface them with the DC bus system. So this is a DC bus system. These all are the so many applications for this one. In the literature to increase the, now I will discuss about the literature. In the literature, so many high gain DC converters are proposed. Similar to the voltage boost techniques, here I am showing the switched capacitor technique and switched inductor, magnetically coupled, voltage multiplier, multi-stage. In out of that, magnetically coupled also transformer based and coupled inductor based. In multi-stage also interleaved converter, cascaded converter, and multi-level converter. These all are the possible high gain DC converters. But our presentation now, I will focus on the more on the magnetically coupled based, magnetically coupled and coupled inductor based converter. This direction I am focusing on in this presentation. So once I will show the different structures like a switched capacitor and switched inductor, how they are boosting the voltage. So first I'm showing the switched capacitor converter. Okay. This is the switched capacitor converter. Here I'm using the more number of the active switches. Here the one side is the input voltage and another side is output voltage. In this converter we can achieve the more than 10 times voltage gain. But here there is the more number of active switches. S1, S2, almost 4 active switches and 4 capacitors are using. Means the driving means the controlling of the all the MOSFETs and switches are very difficult. Require a high complicated driver circuit is required. So as well as there is no more number of capacitors, means instantaneous interest currents are flowing at the time of a sudden on condition. So capacitor act like a short circuit, so interest currents is flowing in the this type of switch capacitor circuits. Okay, here also I'm showing the one more switch capacitor circuit. I'm taking from this one reference too. So these converters are also achieving the high voltage gain, but have so many problems is there. Similarly, the switched inductor capacitor. In the switched inductor capacitor, they are using the active switches and inductors. So separate inductor, L1 one inductor and L2 one inductor. Similarly, in the right side circuit, we can observe that one. Almost 2 active switches and 6 semiconductors and four inductors I am using to achieving the high voltage gain, is more than 10 times. So this type of converters also not suitable for to achieving the high voltage gain, because of the driver circuit is more complex and more number of components also using. Similarly, voltage multiplier circuit. Suppose if you're using any voltage multiplier circuit, the one side is input voltage and another side output voltage. In between, we can place the any multiplier. So these are the 3R voltage multiplier circuits. Suppose if we are adding the any voltage multiplier in between the circuit one, so we can achieve the high voltage gain. Okay. Similarly, cascade converter. Whatever I am discussing, the conventional converter, by conventional converter with series manner or cascading manner, we can connecting also. We can achieve the high voltage gain. But in this one, more number of components and more number of active switches is required. Uh, Now I will discuss about the coupled inductor based converter. By coupled inductor based converter, coupling the one winding to another winding, we can achieve the very high voltage gain. But what is the major problem in the coupled inductor based converters is the leakage energy. So here the leakage energy stored in the primary winding and secondary winding. If you are not restoring that leakage energy properly, that will create the voltage spikes across the semiconductors. Okay. So when we are designing the this coupled inductor based converter, we should concentrate on the leakage energy. If we are effectively recycling that leakage energy, then only it will give the advantages. Otherwise, it will give the less efficiency. Okay. So these are the coupled inductor based converter. But coupled inductor case, what are the advantages? Major advantages by using the lesser number of components. By coupling the one winding to another winding on the same core, we are placing the multiple windings. We can achieve the high voltage gain by using the lesser number of components. Okay. Here I am briefly summarizing all the possible converters, a particular advantages and disadvantages. Measure the conventional converter. High gain cannot be achieved efficiently. Okay, if you are achieving the high voltage gain by using the conventional converter, the efficiency reducing the drastically. We will getting the less than 90% of efficiency. And second disadvantage is either input or output current is discontinuous. Suppose if you are extract the maximum power from this energy sources, non-conventional energy sources or fuel cells, the converter should draw the continuous input current. Then only we can achieve we can extract the maximum power from the PV panels or this non-conventional energy sources. So, but in the conventional converter, major drawback is the either input or output or one of the side is discontinuous. Not discontinuous means, so we need additional parameters like filters. Okay. The switched capacitor also, where placing the reliability of the circuit is very less, and the number of active switches is more. Interest currents at the time of startup, poor voltage regulation. These are the disadvantages in the switched capacitor. Similarly, same disadvantages are occurring in the switched inductor case also. Similarly, voltage multiplier, multi-stage. Majorly, now I'm discussing the advantage of the coupled inductor based converter. Okay. In the coupled inductor based converter, here we can see by using the lesser number of components, we can achieve the very high voltage gain and high efficiency. High efficiency in soft switch type converters, and voltage test on the switches is also less, and high design freedom in this one. And similarly, the energy stored in the what are the disadvantages there in the coupled inductor based converter? The energy stored in the coupled inductor in the form of leakage inductance. If we are using either passive or active clamp circuit, then only we can extract that leakage energy properly to the load. Otherwise, it is dissipated in the form of voltage spikes in the active switches. Okay. Further, I will show that how that leakage energy creating the voltage test on the active switches. So next we will move about the brief about the coupled inductor based converters. So this is the coupled inductor based converter. First I'm showing in the figure A. So this is the basic structure of the coupled inductor based converter by coupling the one winding to another winding. But here also we can achieve the high voltage gain. But here in this converter, the leakage energy of the coupled windings are not recycling properly. So that is creating the voltage spikes across the active switches. So now you can see the figure B. In the figure B, whatever the leakage energy is stored in the primary winding, so that is transfer. Here I am using this number circuit. The red color CP and DP. We can see this one. This is the snubber capacitor and snubber resistor and snubber diodes. Whatever leakage energy stored in the primary winding, that is dissipated in this snubber resistor. So that is not recycling. Means whatever energy each switching cycle, switching on and off condition, whatever leakage energy stored in the primary or secondary winding, that is transferred to the snubber capacitor, but that is dissipated in the resistor. So this is also that much useful. So this is proposed in the reference 43. Similarly, next one they are proposing the active clamp circuit. So here whatever leakage energy stored in the primary winding, that is transferring by using another switch and another capacitor. So additional switch and capacitor, they are transferring the capacitor CA. Okay, this is called active clamp circuit. So similarly, the passive clamp circuit, we are not using any active switch. Here using the passive one diode and one capacitor. So whatever leakage energy stored in this primary winding, that is transferred to the capacitor C3. But in this case, they are not recycling. That is transferred in the capacitor, but they are not recycling properly. So we'll further discuss about the different type advantage and disadvantages of this clamp circuit. These are the each and every possible coupled inductor based converter. Their advantages, disadvantages, and discuss. This is the active clamp technique. These are the short switching techniques, advanced intelligence. Majorly from the literature survey, I'm classifying this coupled inductor based converter based upon the active switch position. Active switch, the few topologies. Here the coupled inductor is connected on one side, and output side. Output side completely they're connecting the active switch. In middle one, you can observe that one. The switch is connected at the middle position. One side is the coupled inductor primary winding, another side is using the coupled inductor secondary winding by implementing the voltage multipliers. In the first case, active switch at the input side. Okay, suppose if you are placing the active switch at the input side and coupled inductor is connected like this. In this case, the coupled inductor, because of this coupled inductor, the input current is pulsating nature. Okay, so if you want to extract the maximum power from the source or PV panels or any non-conventional energy sources, the converter should draw the continuous input current. So here the coupled inductor we are placing at the input side means not that much useful. Means the input current ripple is very high. So that is the causes the we cannot extract the maximum power from the panel. We need additional any filter circuits or any additional capacitor are required at the input side. So these are the advantages of this type of converters. And switch here I'm so comparing in terms of switch voltage stress and switch current and the output side reverse recovery problem of the diode. Here output side D naught is also reverse recovery current is very less. Means the whatever the voltage stress appears on the output side diode is less. But here input side current ripple is more. So some topologies they're connecting the source in the active whatever active switch I'm placing here, that active switch is connected in series with the source. At the time also, when switch in on and off condition, the input current is a discontinuous nature. Discontinuous means again that is the problem. We cannot extract the maximum power from the non-conventional energy sources. Similarly, the output side converter, right side structure, you can see that one. Here the active switch is connected completely output side, means whatever voltage, like a conventional converter. So whatever output voltage achieving at the output side, the same voltage V naught stress is appearing on the diode D naught and V naught stress is appearing on the active switch. So because of this one, we are suppose if the output voltage required is 400 voltage, the 400 voltage stress is appearing on the active switch. Means we are choosing the high rated active switches. If you're choosing the high rated active switch, means on state conduction resistance is very high. Means the losses in the active switch is also more, as well as the diode reverse recovery current. Whatever reverse recovery problem we are facing at the output side diode D naught, if the voltage the reverse recovery problem of the diode is depends upon the voltage stress. If the voltage stress appearing on the diode is more, means obviously it's facing the reverse recovery problem. This side converter is facing the reverse recovery problem at the output side, and voltage stress on the switch is also more. But here advantage is the input current is continuous. Here whatever source I am connecting, source in series with, we are connecting the inductor, not connecting the coupled inductor. If we are placing the coupled inductor drawing the pulsating current, but if we are placing the inductor, means it is draw the continuous input current. But this is the advantage. But one disadvantage is, suppose if the middle switch connection, if the switch is connected, one side is coupled inductor, another side is another coupled inductor. I'm connecting the inductor in series with the source. These type of structures will give the continuous input current as well as the reduced voltage stresses. Whatever voltage stress is appearing on the output side, 30% of stress means, you suppose if you're getting the 100 voltage at the output side, only 30 voltage stress is appearing on the active switch. Similarly, diodes also. So reduced voltage stresses is appearing on the active switches. So this type of middle switch connection is more advantageous than the remaining possible way of connections. Okay, so that's why I'm further moving on the this middle switch connection structure. So the desired features of the coupled inductor based high gain converter as follows. The converter has the feature of, first one, input current should be continuous, and second one, the effectively recycling the coupled inductor leakage energy to the load. Third one, reduced semiconductor stresses compared to the similar topologies reported in the literature. Okay, once we are proposing any topology, means we should compare our proposed topology with a similar topologies reported in the literature. So okay, then only it will be acceptable. Okay, then the ZVS operation of the active switches. If you are suppose nowadays we are using a very high frequency switching frequency. If you are going the high switching frequency, means switching losses is more. So we can reduce the switching losses by making the topology can operate at the ZVS nature. Okay, zero voltage switching at the input active switches as well as the output side diodes also. And improve reverse recovery performance of the output side power diodes. Okay, so the reverse recovery performance of the output diodes. Previously, I'm told output side diodes are facing the severe reverse recovery problem. So our next or proposed converter should be reverse recovery problem mitigating. Okay, minimum we can we have to reduce the reverse recovery problem. Okay, now I'm proposing the one of the converter. This structure, this structure, this topology is accepted in the IEEE transaction in circuit and systems too. So previously, whatever drawbacks I'm highlighted from the literature, to overcome the drawbacks, here I'm proposing the one structure. In this one, I'm placing the two boost stages. Okay, boost stage one, a red dotted line, I'm indicating the boost stage one. Okay, this inductor by using the another blue dotted line. Okay, showing the boost stage two, and one voltage multiplier I'm adding at the output side. Okay, in middle switch, I'm placing the active switch. Okay. Here I'm using the two boost stages and one voltage multiplier. Boost stage one is almost similar to the conventional boost converter. The conventional boost converter source in series with the inductor. So that's why it's drawing the continuous input current. So it will suitable for the non-conventional energy sources. So inductor is connecting in series with the source. And boost stage 2, I'm using the coupled inductor. Boost stage 2, one winding I'm using in the coupled and boost stage coupled inductor one winding, and another winding I'm using the voltage multiplier circuit. Okay, so here this both the boost stage 1 and boost stage 2, I'm derived by using the single active switch. So entire topology I'm using the single active switch, two boost stages. Boost stage 2 here in the two purpose. One is the boosting the voltage as well as the whatever leakage energy stored in the coupled inductor. So primary winding and secondary winding. By using the diode D3, I'm transferring the capacitor C3. Okay. Here the boost stage 2, I'm using the two purpose. One is the boosting the voltage as well as the leakage energy effectively recycling to the load side. Okay. This is transferring capacitor C3. And to improve the further voltage gain, I'm adding the one more voltage multiplier by using the coupled inductor winding and a secondary winding. Here I'm placing the this pink color showing the dotted line showing the voltage multiplier. Okay, so this connector is giving the reduced voltage test. I am on the active switch. I'm connecting not connecting completely at the output side. I'm not connecting the input side. In between, I'm placing the active switch. So here the voltage test appearing on the active switch is 33% of output voltage, and similarly current test also very less on the active switch. And the total diode voltage tests and total input current is continuous in this one. Now, so similar structure here I'm showing this one. Here in between, here I'm not showing recycling the coupled inductor leakage energy. So in the point here, so above circuit we can see that one, and in between both at middle point I'm taking the diode D3. So here whatever leakage energy stored in the primary and secondary that is transferred to the capacitor C3. So similar one of the proposed converter here I'm showing. This one the leakage energy of the primary winding not transferred to the any capacitor. So whatever leakage energy stored in this primary winding that will create the voltage spikes across the switches. So this type of converters is not that much useful. So how the effect, how the leakage energy is affecting on the switches in the okay, we see the hardware diagram also further. So in the proposed first converter, these are the advantages. Single power switch we're using. Okay, low voltage test on the active switch, and the converter has the feature of input current continuity and effectively recycling the coupled inductor primary and secondary leakage energy to the load, and reduces the aggregate of the diode and active switch voltage tests compared to the similar topologies reported in the literature. And third one, the maximum gain of the converter can be adjusted by changing the turns ratio of the coupled inductor. Here I will discuss about the typical waveforms of the proposed converter. First one, you can see this one. The total our waveforms I'm classified into the total 5 modes. Okay. Out of these 5 modes, 3 modes are the just transition modes, 2 are the steady state modes. Okay. So here first we can see when the switch is on condition, when the switch is on at the time inductor, okay, charge it through the active switch, inductor L1 is charging. Similarly, the here say at the same time VC1 is act like a voltage source. At the time the through the active switch through the inductor, coupled inductor, VC1 coupled inductor and switch. So coupled inductor also charging at the time of turn on the active switch. Okay. When the switch is turn off, suppose this is the when we are coming to the mode 3, when the switch is turn off At that time, whatever leakage energy stored in the primary and secondary winding through the diode D3, here so see the ID, the diode D3 current. So when the switch is active, switch is off, at the time the both the leakage energy stored in the both the windings through diode D3, D3 transfer to the capacitor C3. Okay. So here we can observe the diode D3 current is little bit peak in nature. So shortly it will transfer to the capacitor C3, but that is the in the acceptable range only. Okay. So this is transferred to the capacitor C3. So that C32 that is transferred to the, and then the next mode, in the mode 2, C32 to C2. Okay. In the mode 5, that leakage energy transferred from C2 to load. That means whatever leakage energy we're not using, like some topologies they're using the snubber circuit. In the snubber circuit, they are dissipating that leakage energy in the snubber resistor. But in our case, we are not dissipating that energy. That is effectively transferred to the load side. Okay. This is the mode 1 and mode 2, mode 3 and mode 4. Mode 1 indicate the turn on condition. Mode 4 and 5 indicate the turn off condition. Okay. So by applying the volt second balance equation across the inductor, we can achieve the equation like that, like a conventional converter. Vc1 equal to V in by 1 minus D. Okay. The voltage appears across the switch one. Similarly, here our nature is the converter is quadratic boost converter. Means here Vc1 voltage is V in by 1 minus D. Similarly, I were applying the volt second balance equation across the coupled inductor. We can achieve the Vc3 voltage. Vc3 voltage is V in by 1 minus D volt D whole square. Okay. First boostage will give the voltage V in by 1 minus D. Second boostage will get the V in by 1 minus D whole square. And additionally we're adding 1 volt multiplier. So by applying the after that deriving the equation, we will get the gain 2 plus nk. Means Vc2, that we are getting the Vc2 voltage 1 minus D whole square, and after that we're adding the voltage multiplier, we can get the 2 plus nk. Means n equal to 1, a coupling coefficient of coupling k, suppose if you're taking almost 1 at the 3 times, so means the gain is multiplied. Okay. Either quadratic boost as well as the multiplied gain 2 plus nk into 1 minus D whole square is the gain of the converter. Here the switch remaining factors I am deriving for the proposed topology. Here I am comparing the proposed topology in terms of the number of the components, voltage gain, switch voltage stress, and the total diode voltage stresses. So the first one is our proposed structure, and remaining all are the similar topologies reported in the literature. Okay, so same topology structure I am showing in the pictorial manner. Okay, so here the curve voltage gain versus duty ratio. The red one is indicating the proposed converter. The proposed converter is giving the very high voltage gain compared to the other topologies. But in the blue, up to 0.65, our proposed converter is better. Red one is better. After that, the black one is better, but the black color topology is giving the discontinuous input current. Means in that case, the coupled is connected in series with the source. Okay, so that one need any additional circuits to get the continuous input current. Similarly, active switch voltage stresses. So here we can see the red one is indicating the proposed converter switch voltage stress. If switch voltage stress comparatively other topologies, our proposed topology is giving the less switch voltage stress. Here you can see. So if the switch voltage stress is less, means we can choose the low rated switches. Low rated switch means the low rated switch on state conduction resistance is very less. Means the efficiency of the converter is improving. For the same voltage gain compared to other topologies, we can choose the low rated active switch. Because of that low rated active switch, on state conduction resistance is very less, then we can get the more efficiency. Okay. And similarly, you can cover comparing the sum of the diode voltage stresses. Diode voltage stress also proposed converter is giving the very less. Here we can see the red one is the proposed converter operating range up to 0.5. Within the 0.5 range, the red color one proposed converter is giving the better diode or some of the diode voltage stresses. And similarly, the figure B, you can see that one by changing the number of turns, we can achieve the better whatever voltage gain we required. We can by change the turns ratio, secondary winding turns ratio can improve. We can get the more voltage gain. Previously I'm showing the effectively recycling the leakage energy. Our topology I'm making that headline effective recycling topology. Means one of the topology, if they are not effectively recycling that leakage energy, that is, so in the figure A we can observe that one. Here I'm showing the output voltage and switch voltage hardware. This is the scope waveform. In the scope waveform we can say that one, this is a little bit peak in nature. When the switch is on, when at the time we can get the 15 voltage spike. Okay, so in this case the leakage energy of the coupled inductor is not recycling properly, that is creating a little bit spike across the active switches. So similarly, the proposed converter, we can observe that one almost 1 or 2 voltage only. That when the switch is turned on, at the time voltage spike is smooth waveform we are getting. Switch voltage waveform. Okay, output voltage also very smooth. This one is the right side figure B is the effective recycling the leakage energy. In this one we are not if we are not recycling that leakage energy, that is creating voltage spikes like this. Next, this topology I'm implemented at the power level of 40 watt. So just this can scale up. This topology can scale up to 501 kilowatt any PV panels based upon any power level. But based upon the I'm making with a 40 watt prototype. Okay, this is the prototype. I'm using the analog controller. Here I am showing the two. One is the power circuit, another one is the analog controller. Okay. There is input voltage range 7 to 16 voltage, output voltage 10 volts. So even 7 volts or 5 volts also this converter input voltage 5 volts and output voltage 20 volts, means up to 15 times voltage gain also we can achieve this topology. This is the frequency 108 kilohertz, and these are the capacitor parameters, switches and diodes I'm using. So here I'm seeing the controller circuit. This is the power circuit. By analog circuit, nowadays they're using almost digital DSP controller and FPGA controller. But analog controller is very easy. So by making the simple TL494 IC, so that IC we are taking the output voltage feedback. This need the 2.5. This IC required the 2.5 voltage range feedback voltage. So our output voltage is almost 100 voltage I'm getting. I'm gonna scale down that voltage by using the potential divider. Here I'm not showing the potential. Here by placing the potential divider, I'm step down that voltage to 2.5 voltage range, and I'm giving the feedback to the IC TL494 IC. I'm giving. So in this TL494 IC, we can get an oscillator. Oscillator means we can get the one ramp cycle by making the one capacitor and resistor. So by making the capacitor and switches, 3 volts magnitude, one ramp signal we are getting. That ramp signal is comparing with our constant signal, whatever the feedback signal. So we are getting the PWM pulses. Okay, this is by using the simple TL494 IC, we can easily implement the closed loop control of the proposed circuit. Any circuit, any high gain converter, we can implement by using this TL494 IC. Okay, these are here I'm placing the small capacitor. This all the control circuit capacitor resistor are low rated switches only. The power circuit one only we are getting the little bit high currents. These are experimental waveforms. Okay, whatever I'm achieving the simulation, same smooth waveforms I'm getting in the experimental also. Okay. These are the efficiency analysis. Okay, here I'm showing the efficiency versus input voltage. If the input voltage I'm designed for the 7 volts to 16 voltage range at the power of 40 watts output. At 40 watt power, I'm changing the input voltage from 7 voltage to 15 voltage. During that range, the efficiency, so when the gain factor is more, at the time the efficiency is very less. If the gain factor input voltage is increases, means the gain factor is less. At the time the efficiency we are getting the more. But in this case, at operating at the generally rated condition 100 watt at 10 watts, 10 watt, 40 watt power. At 10 watt, I'm achieving the almost 93% and 94% of efficiency. Okay, the blue one indicating the theoretical efficiency, and the red one indicating the experimental efficiency. Similarly, I'm varying the output power, efficiency versus output power at stable input voltage. Here I'm showing the 10 volts input voltage, constant 10 volts input voltage. I'm changing the load resistance. Load resistance means I'm changing the load power. Okay. Here I'm changing the 10 watt to almost 45 watt power. I'm varying. So varying doing that one, this is the efficiency variation. At rated power, I'm almost getting the 93-94% efficiency. With leakage energy recycling, here I'm showing the two efficiencies, with leakage energy recycling and without without recycling the leakage energy. If the leakage energy is not recycling properly, at the time we can see the at the rated power at 40 watt power, more deviation is there. Okay, at low power, the whatever leakage energy stored in the coupling is very less, so that impact is very less. Okay, here I'm getting the almost similar efficiency with leakage energy recycling and without properly recycling the leakage energy. The efficiency impact on the efficiency is very less at the low power. But at the rated power and high power condition, with recycling the leakage energy and without recycling the leakage energy, we can get the more deviation. Almost 2 watt power is wasted in the active like as voltage spikes. Okay. These are the advantages and the summary of the proposed converter. They effectively recycle the coupled leakage energy to the load by using the passive clamping technique. And the performance of the converter with and without leakage energy recycle is compared. The configuration provides the lowest switch voltage test and the total diode voltage tests compared to the similar topologies available in the literature. At rated power 40-watt condition, the converter gives around the 93.4% of experimentally measured efficiency with leakage energy recycling and 90.2% without leakage energy recycling. Okay. These are the advantages, but one is the major, we can observe that one is the major disadvantage in this converter is we are not all the active switches, all the active, whatever the active switch and diodes are hard switch in nature. I'm not achieving the soft switching. Okay. But all the switches and diodes are hard switching. Suppose if you are going to the almost, I'm using the 100 kilohertz frequency. If you go to the further, if you're increasing the frequency, so switching losses, the turn on losses and turn off losses is very high. Okay. uh, Here I'm not achieving the ZVS nature, and also if the voltage gain also up to 15 times it is suitable. If you want to require the 20 times voltage boosting technique, of course 20 input voltage is 20, output voltage is 400, we require the gain factor 20 times. At the time also this topology is not suitable. It means if the gain factor is up to 15 times only, it's good. If you want to require more than, then I'm discuss about the so here the drawback is all the switches and diodes are hot switched and the gain factor up to 15 times also it is suitable. So next I am proposing the new topology. Hello, are you following? Hello.
Yes, sir.
Okay, madam. Whatever the previous topology, okay, good, but there are some drawbacks were identified in that one. What are the drawbacks? In all the active switches and diodes are hard switching nature. Hard switching nature, if you are going increasing the frequency from the more than 100 kilohertz, at the time switching losses is dominating. Turn on losses and turn off, both the cases are hard switching nature. So turn on and turn off loss of the active switches and diodes are more. Okay, so this is the further modification in that topology. Here I'm taking the similar structure, two boost stages, input is inductor I'm connecting the same input boost stage 2 also similar, but I'm changing the voltage multiplier 1 and voltage multiplier 2 is a voltage multiplier. I'm taking the one more auxiliary switch, active switch and auxiliary switch. By using this auxiliary switch and this coupled inductor, I'm properly choosing that coupled inductor magnitude, we can achieve the ZVS nature of the switch and auxiliary switch, and as well as the two voltage multiplier, two boost stages and two voltage multiplier. So here the boost we can achieve the voltage gain is very high compared to previous topology. Okay, so this one is giving the ZVS nature as well as the boost factor is also more. This topology is recently published in the IEEE Transaction in Power Electronics in 2023. Now we will discuss about this topology. Those who are recently joined in the PhD or these topics are very easy topics, so we can go through this one. If you have any doubts, we will discuss that last. This converter gives the following advantages: the ZVS operation of the active switch and output side diodes with relatively low. Okay, these are the major advantage in the proposed topology. The ZVS operation of the active switches and output side diodes with relatively low mutual inductance of the coupled inductor. Okay, in this case, previous topology I'm using the coupled inductor magnitude 200 microhenry, but in this case I'm reducing that to 20. Okay, the mutual inductance is very less, as well as the in this one improving the reverse recovery performance of the output side diodes. So yeah, I'm placing the leakage energy. Okay, whatever the reverse recovery problem of the output diodes means, when the diode is off, at the time the current is falling, negative peak we are getting. So when the diode is falling, current is falling with some, if the diode current is falling with some slope, means we can improving the reverse recovery performance of the output diodes. The proposed converter also, I'm improving the reverse recovery performance of the output side power diodes by limiting the current falling rate using the leakage inductance of the coupler, and effective recycling of the leakage energy to the load using the active clamping circuit. Previously, I'm using the passive clamping circuit. Here, I'm modifying to the active clamp circuit. And similarly, reducing the semiconductor stresses compared to the similar topologies reported in the literature. This converter also giving the continuous input current that is suitable for the non-conventional energy sources. Okay. These are the typical waveforms of the proposed converter. Typical waveforms of the proposed converter here. So here the total steady state waveforms I'm classified into the 8 modes. Okay, out of these 8 modes, 2 modes are the steady state modes. remaining all are transient modes. Okay, if you are observing the waveforms properly, then only we can identify this all the modes. Okay, so when the suppose from the mode 1 onwards we will discuss. If I am discussing the each and every mode diagram, it will take the more time, so I'm briefly summarize the this mode diagrams. Okay, so so here we can see that one, the blue color indicating the main switch turn on time, and 1 minus dt time indicating the auxiliary switch turn on time. Okay, then the auxiliary switch is off at the time, I'm considered as the mode 1. Okay, so here start means after this one we start mode 1. Okay, when the auxiliary switch is off means the snubber capacitor. Okay, and the switch where obviously any, if your switch is buying means obviously the internally we're placing the one MOSFETs. Internally one diode is there and the internal capacitor also there. That capacitor is called body diode or internal diode, and that capacitor called snubber capacitor or internal capacitor. Okay, when the switch is off means the snubber capacitor discharges from charges to VC3 voltage. When the auxiliary switch is off means at the time the snubber capacitor, this snubber capacitor value is very less, so very instantaneously it will charge. Okay, so here you can see that mode 3 also very less, instantly charged to the VC3 voltage, and whatever the voltage previous VC3, there is the snubber capacitor of the main switch discharges from the VC3 to 0. Okay. So in the mode 2, when this current is reaches to 0, at the time the internal diode of the auxiliary switch come into the picture. Okay. So when the switch is when the auxiliary switch is turned on, when you are giving the pulses to the main switch DTS, here we can observe that one waveforms. Then we are giving the triggering pulse to the main switch. At the time the current is flowing through the opposite direction. Opposite direction. So the voltage is positive, current is negative. Means this is the ZVS turn on. Okay. So the current is flowing in the opposite direction. Here we can see that I'm highlighting the switch is turned on with the ZVS nature. Here by properly how can we design that the ZVS nature? We can discuss in the equations. Next one. At the time the current is flowing to the opposite direction to the body diode. Okay. Similarly, the turn off also, here we can see in the waveforms. Okay, in the waveforms we can turn off condition also, we can get in the near to ZVS turn off. This is the turn off condition with some slope. I'm getting the turn off. Okay, ZVS turn on is complete ZVS turn on and nearly ZVS turn off, and we are achieving. Similarly, the auxiliary switch also, when the switch is off, at the time the current is flowing to the opposite direction, negative direction. So this is also achieving the ZVS turn on, and turn off also partially I'm getting the ZVS turn off. Okay. Similarly, the diodes also turn on. When the diodes is on, you can see that one D3 and D4 currents. Okay, when the switch is on, at the time the current is 0, so means the diodes are on with the ZVS turn on. Similarly, then the diode is off, at the time I'm placing the winding. Here suppose any diagram we can observe that one D0 in series with C4 in series with the coupled inductor secondary winding. So when the diode is off, at the time the current instantaneously it cannot fall. So it is falling with some slope because of the leakage energy of the winding. Suppose if we can see the any diode D3 diode in series with the D3 diode in series with the territory winding. That means when the diode is off, at the time the current is not instantaneously falling to the 0. It is falling with some slope. Here we can observe the diode D3 and D4 currents. It is falling with some slope, means the reverse recovery performance of the diodes is improving. Suppose if instantaneously falling to the 0, we can get some negative peak. That it's falling to 0 and it is going to the negative, we'll get some negative peak. Okay, so in this case we are not getting like this. It is falling with some slope. So that means that we are achieving the reverse recovery performance of the diode D3 and D4 and D0 also improving, and as well as the reduced voltage stresses. The reverse recovery performance also depend upon the voltage stress. Here also whatever output voltage V0 I'm getting, same voltage stress is not appearing on the D3 and D4, reduced almost 50%. Here I'm getting the 400 voltage means output means almost 200 voltage or 210 voltage stress is appearing on the D3 and D4 and D output set diodes. So if the reduced voltage stress is appearing on the diodes, means that is also one of the reason to improving the reverse recovery performance. And second cause is the this falling with some slope, means that is also improving the reverse recovery performance of the output set diodes. Similarly, the output diode D0 current also we can see that we are achieving ZVS turn on, as well as it is falling with some slope, means the reverse recovery performance of the output side diode is also improving. This is the brief summary about the waveforms. If I am discussing the each mode and each operation and the total 8 modes diagrams, this one, it will take more time and it is making you to clumsy also. Okay. But this is the suppose if you are proposing any topology, this is the basic structure. This is the nature to analyze the waveforms. Okay. If you want to more details about the topology, you can cite my, you can go through with my paper and the IEEE transaction power electronics. You can get the brief description of the each and every mode and how the current flowing diagrams, how this number capacitor working in this topology. Next, I'm applying the by applying the volt second balance equation across the inductor. I'm getting the Vc1 equal to Vg by 1 minus t. Suppose same thing like that. By applying the volt second balance across the coupled inductor, we can get the Vc3 equal to Vc1 by 1 minus t means Vc1 equal Vg by 1 minus t. So Vc3 equal Vg by 1 minus t whole square. Means here also quadratic boosting I'm achieving. So similarly, here we can see the Vc2 and Vc3 equations. Similarly, the converter voltage gain V0. Here I am deriving the voltage gain of the converter in terms of coefficient of coupling, leakage inductance, and in the switching frequency and the load current. By all the factors, I am deriving the voltage gain. Okay. So for ideal case, ideal voltage gain means the coefficient of leakage equals 0 means ideal condition means 100% coupling the one winding to another winding means k equal to 1 condition. Here the boost factor 2 plus 3 n by minus n minus d by 1 minus d whole square. In the proposed converter, ZVS nature is I told achieving. What are the factors impacting on the ZVS nature of the converter? Here we can see that. This is the final equation. I'm discussing about the how I'm deriving. It will take the more number of steps, but I'm final equation. This is the LM, the magnetizing inductance of the coupled inductor should be more than the load RD by 2 into 1 minus d into 2 into 1 minus d by g square into 6 minus g is the gain factor. Fs is the switching frequency. R is the load resistance. Here I'm drawing one curve. The red one is indicating the boundary between the hard switching and soft switching. This is the boundary line. Okay. The boundaries depends upon the output power, magnetizing inductance, and switching frequency. In our this converter, I'm implemented at 250 watt power. Previously, I'm implemented for first converter 40 watt power. Now I'm increasing the little bit more power at 250 watt power at a 20 microhenry inductance. Almost this is here our operating point is there. Okay. This is the soft switching boundary. If the operating point is near to soft switching boundary only, we are getting the more efficiency. Okay. If the operating point is far away from the hard switching zone or far away from the soft switching zone also, we are not getting the good efficiency. Okay. The proposed converter is completely depends upon the means one particular power only, constant power only. This is the better sort of topology. Means then the topology is operating near to soft switching boundary. At the time, this converter is giving the higher efficiency. Okay. Why it should operate at the continuous near to boundary, we'll explain it further. Comparative study. If I am proposing any topology, means that topology should be compared with recent topologies. Then only the topology is acceptable. Here I am comparing the proposed topology in terms of all this is the IEEE transactions and the IEEE journals. Okay. Similar more number of components and the voltage gain, voltage stress on the switches, and aggregate of the diode voltage stress and soft switching nature. Based on these parameters, I'm comparing the proposed topology. Compare number of components also here. I'm getting the 14 components. Okay, means each winding I'm taking as a one component. Primary winding one, secondary winding, tertiary winding, like that. Okay. Here remaining all the components are using 15, 21 more number of components to achieve the same voltage gain. These are the further topologies. So whatever the topologies I'm showing shown in the table, the pictorial manner I'm showing here the voltage gain versus the duty ratio. I'm drawing one curve. Okay, the red one is indicating the proposed converter voltage gain. Okay. So comparatively, the proposed converter is giving the higher voltage gain. Okay, that one is almost upper than the remaining curves. And similarly, the switch voltage stress. Okay. Whatever voltage stress is appearing on the active switch, the red one is indicating the active switch, our proposed converter switch voltage stress. Okay. Our red one is almost better than the remaining topologies until to the operating point. Generally, high gain converter is operated near to between the range of 0.5 to 0.6 only operating. Up to that point, our proposed converter is giving the better switch voltage stress. Okay. If the switch voltage stress is less, means obviously we can choose the low rated switches. And low rated switches means the switch on state conduction resistance is very less. So efficiency also of the converter is improved. And similarly, some diode voltage stress. If the diode voltage stress is stresses is depends upon the reverse recovery problem of the diode. If the sum of the diode voltage stress on the diodes is less, means obviously reverse recovery performance of the diodes is good. Here also the proposed converter is indicating the red one. Proposed converter. Comparatively other topologies, the proposed converter to some of the diode voltage stress is reasonably better. One or two topologies giving the better. Suppose this green blue dotted line one is giving the better, but this converter is giving the coupled integrator is connected in series with the source. So that means it is drawing the discontinuous current from the source. To extract the maximum power from the non-conventional energy sources, the converter should draw the continuous input current. But these are the drawback in that type of that converters. So our proposed converter is better than these converters also. The gain of the converter also can improve by using the number of turns ratio, n equal to 1, n equal to 3, and n equal to 4. These are the different turns ratio. Okay, the gain of the output converter can achieve the better voltage gain by changing the number of turns. Here, first topology I'm showing the 1:2 turns ratio, but in the proposed converter you can see the 3-winding coupled inductor I'm using NP and NS NT territory 3-winding coupled inductor I'm using. All the turns ratio is 1:1:1. Okay, but why I'm going to the 3-winding coupled inductor instead of 2-winding coupled inductor? Okay, if the 2-winding coupled inductor also we can measure the 1:2 turns ratio. Okay, if you're making the 1:2 turns ratio means we can obviously increase the gain of the converter, but I'm not choosing the turns ratio 1:2, but instead of that 1:2 turns ratio means instead of by properly placing that extra turns to in the another place in the circuit, we can achieve the higher voltage gain. Okay, so if the 1:2 turns 1:1 coupled inductor converter, I'm placing the 1:2 turns ratio here all the converters, and the proposed converter 1:1:1 3-winding coupled inductor means I'm placing that instead of 1:2 winding, the size of the coupled inductor is same. If the coupled inductor with the 1:2 turns ratio or 1:1:1 turns ratio, the comparatively the size of the coupled inductor is obviously same. But if we properly placing that third winding in the coupled inductor another proper place, we can achieve the higher voltage gain than the 1:2 winding coupled inductor. Here we can see the for duty ratio d equal 0.4. I'm comparing the coupled inductor with 1:2 turns ratio topologies. Our proposed converter, those converters, this also 26 also other topology proposed. So these topologies are giving the better voltage gain, 12.8 times at d equal 0.4. I'm using the 12.8. Remaining all are giving the lesser than that only. Due to that one, the efficiency, theoretical efficiency, these are at that operating point, and we cannot compare all the experimental efficiency, but theoretical efficiency I'm comparing. Proposed converter is giving almost 96.1 efficiency, then is a better efficiency than the remaining converters. Now we will discuss about the design of the core selection. Coupled inductor, how can we design the coupled inductor? First of all, when we are choosing the coupled inductor, we should go through the area product. Okay, so from theoretical formula, this is the theoretical formula available in the Ericsson textbook. Ericsson standard textbook is there. In the textbook, the design formulas are then mentioned. From that one, I'm taking that formula. So area product of the coupled inductor, I have primary winding RMS current and secondary winding and tertiary winding current into that peak primary winding peak current will multiplying with the magnetizing inductance, and these factors, a window factor and maximum flux density and current density, these factors multiplying, we can get the area product. Okay, I was choosing whatever we want to design the coupled inductor, that core area should be more than this one. Here I'm choosing the coupled inductor build. I'm using the EE424215. This is the I'm using this core. This core area product is 3.234 centimeters for 4. So this area product is more than our required area product. Then only this is the winding will be fit within the core. Okay. Otherwise, if the required turns and winding is more than the core. Okay. So when you are designing at the time, you choose the area product of the core. Okay. Then I'm choosing the number of turns. Based upon that one, I'm designing based upon the magnetizing inductance. Okay. Once by using the soft switching nature, we can choose the how much magnetizing inductance is required. Based upon that magnetizing inductance and our output power, we can choose the number of turns. Number of turns here and get the 13 turns. Okay. NP and NS all are the same number of turns, but number of parallel lines is different. Okay, in the primary winding current and secondary winding and tertiary winding, whatever the current is flowing is completely different. Primary winding is obviously more current than the secondary and tertiary winding. So number of turns is same, but number of parallel paths is different in the each winding. Similarly, the area graph. Okay, if you are placing the properly that area graph, then only the air should not be saturated. Otherwise, when we are going to the near to the rated power, the core will be saturated. Okay, so here also by using this formula, we can choose the area gap. Area means air gap within the core material. Then we can brief discussion about the losses. Okay, majorly when we are calculating the total theoretical losses. Uh, First of all, active switch losses. The active switch losses contain the majorly two parts. One is the conduction losses, second one is the switching losses. The proposed conduction losses in the data sheet, whatever switch we are selecting in the data sheet, they will mention the odd on-state conduction resistance for particular current. For this much current flowing in the switch means there is corresponding the on-state RDS on they will mention. Based upon that one, I am calculating the switch conduction resistance. Similarly, switching losses or proposed converter ZVS turn on I'm achieving, but turn off is partially ZVS turn off I'm achieving. So the turn off losses obviously somewhat is there in this one. Similarly, the auxiliary switch turn on losses and turn off losses, and similarly conduction loss I'm calculating. Then we will go to the coupled inductor losses. Coupled inductor losses majorly two factors is there. One is the conduction losses. Okay, all the windings here P is primary, secondary, and tertiary conduction losses, and J equal to 0 means DC losses and AC losses. Okay, when we are calculating the losses means in this one, what is the DC part of the losses is there, and AC ripple on the top of the DC, some AC ripple is there. So we should consider that AC ripple also. Okay, then only we can accurately calculate the losses of the converter. Okay, the AC ripple resistance we can measure by using the LCR meter. By like a conventional multimeter, we cannot measure the high frequency. Suppose 100 kilohertz. Here, so suppose some cases there is isolated converter. Isolated converter means they are using the AC nature of the in the coupled inductor or transformer, that current is flowing in the AC nature. Okay, suppose in this case we are using high frequency means fundamental component is 100 kilohertz means our third harmonic and fifth harmonic and sixth harmonic component 700 kilohertz, 800 kilohertz also frequency components. That corresponding resistance also we can calculate by using the LCR meter. By using the conventional meters we cannot measure this high frequency resistance. Suppose the fundamental component PS1, PS means the ripple fundamental component. Corresponding the losses, I'm calculating this one by the LCR meter 2.93 watts. Similarly, the core losses also a major part. The core losses completely depends upon the flux nature. Okay? Here I'm calculating the maximum flux flowing in the core. Okay? In the core data sheet, they will mention the flux corresponding to losses. Okay? Losses per kilowatt watt. Okay, we know the volume of the core, correspondingly the flux corresponding losses we will multiply, we can get the core losses by using the data sheet only. Similarly I'm calculating the inductor losses also. Then we're going to the diode losses. Diode loss also based upon the data sheet, we can multiplying the diode current and diode resistance, on state resistance, and forward voltage drop, we can get the diode losses. Okay. Similarly the capacitor losses, this one. Here I'm showing the some pictorial manner with rated power at 250 watt power and 50 watt power. Left side one is showing the at the 250 watt I'm getting the 12.37 watt power. At 50 watt I'm getting the 6.3 watt power. Okay, losses. These are the losses. So when the at rated power, the major losses is the diode losses. Here the blue color, light blue color is showing the 43% of diode losses at the rated power. At low power condition, the major contribution is the green one, 45%. That is the inductor losses. Means at low power, constant loss is dominating the remaining losses. Okay, so here the efficiency is almost I'm getting the 86% at low power, but at the high rated power I'm getting the 96%, 97% efficiency. Okay. So here I'm so when the power is changes means the operating point, what in the ZVS nature, whatever I'm getting the boundary line. So when the power is reducing means the operating point shifting far away from the boundary line. So if the operating point is far away from the boundary line means the efficiency is not that much good. So if whatever point is we're choosing near to that boundary line only, we're getting the better efficiency. Okay. So it means rated power condition means at the time only the operating point need to the boundary line for the design specifications. So if for shifting suppose I'm operating at the low power condition, at the time the operating point is shifting far away from the boundary line. That's why I'm getting the very low efficiency, 86 or 87% of efficiency. These are experimental verification. In previous one, I'm implemented the analog controller, but here I'm implemented the using the digital controller DSP board. This is the DSP board. These are sensors, voltage sensors. These are the current sensors. Here to measure the each and every MOSFET current. Rogowski coil. Here Rogowski coil means this is the advanced one. By using the small ring type coil is there. So each diode each limb, we can place that Rogowski coil. We can measure the each diode or each and every part, even capacitor current also. Whatever the small limb is there, now we can measure the circular that Rogowski. By using that Rogowski coil, we can easily measure the current values. This is the laboratory prototype. This is the controller. This is the voltage measure. Here I'm using completely isolated probes. This one voltage measurement means isolated probes. These are laboratory setup. This is operating at a 250 watt power and input voltage is 25 to 35. Output voltage 360 volts. Frequency 70 kilohertz. These are the parameters. These are the experimental results of the proposed converter. Here you can observe that one. Whatever ZVS nature and whatever the diode on your ZVS turn on of the diodes also, whatever is showing, same waveforms I am achieving the experimental also. Here we can show the switch is turn on under the ZVS condition and the turn off I'm achieving the partial turn off of the ZVS turn off of the active switches. Similarly, auxiliary switch also the turn on ZVS turn on I'm achieving, turn off also partially turn off I'm achieving. This is also, you can see that one diode 1, diode 2 voltages. And here we can observe the D4 current. Diode D3, D4 current is turn on with the zero nature. When the switch is on, at the time the current is rising from the zero. Okay, so this is the ZVS turn on, and reverse recovery performance of the diode is also good. Means the current is falling with some slope. Here we can observe that one. The current is initially not falling; it's falling with some small slope. So the current falling rate controlled by using the leakage inductance coefficient. So here also the leakage, the reverse recovery performance of the diode is also good. Here we can also see that one diode D5, means output side diode. Majorly high gain converter output side diode only facing the severe problem of the reverse recovery problem. But in the proposed case, the output side diode is ZVS nature and the current is falling with some slope, means reverse recovery performance also we are improving, and reduced voltage stresses also appearing on the diodes. So where output side diode is not facing the that much severe problem of the reverse recovery problem. These are the experimental waveforms. And next one we'll briefly discuss about the efficiency analysis. Here I'm showing the efficiency versus output power. Okay, so here red one is indicating the theoretical efficiency and blue one indicating the experimental efficiency at 70 kilohertz frequency. At 70 kilohertz frequency, this is the efficiency. At rated power, we are achieving the almost 94% efficiency. At 100 kilohertz, we are achieving the almost 96% of efficiency at 250 watt power. But when the power is reducing, efficiency versus output power we're drawing, then the power is very less, means 50 watt, 100 watt. At the time, the efficiency is very less. Okay, why? Because the operating point operating far away from the boundary line. To improve to shift that operating point near to boundary line, I'm increasing the switching frequency. But here, general operating frequency 50, 60, 70 kilohertz. Here, this blue color indicating the falling. Okay. To improve the efficiency at the low power condition, I'm increasing the switching frequency. By increasing the switching frequency, means the operating point is shifting near to boundary line. So that's why I'm achieving the better efficiency, more than 90% efficiency. Also, at low power, I'm getting 130 kilohertz. Okay, above that one, we're getting the efficiency, better efficiency. Similarly, I'm comparing the efficiency versus output power at 100 kilo, comparing the 100 kilohertz and 70 kilohertz. Our proposed converter is ZVS nature. Even though if I'm increasing the frequency also, remaining losses, we're getting the better efficiency. Efficiency is almost little bit improved. Why? Because our proposed converter is soft switching nature. The operating point is under hard switching. Suppose if the switches are hard switching, if the switching frequency increases, means the efficiency will reduce. But in case ZVS topologies, these are the main advantage. If switching frequency increases, means obviously the efficiency of the converter is improved. Next, we will discuss about the small signal modeling. Small signal modeling of the proposed converter. This is our one of the proposed converter. This is similar to first topology. 2 boost stages and 1 voltage multiplier here. So this is the on condition and off condition proposed topology. These two conditions, I'm taking the number of the state variables. First we will check about the large signal modeling, then we will go to the small signal modeling. In the last signal modeling, I'm taking all the state variables. Total, I'm choosing the 8 state variables. Out of this, the state variables of the proposed converters are the current flowing through the inductor, the coupled inductor, leakage, and magnetizing, and secondary winding currents are the one set of the state variables. And another state variables are the capacitor C1, C2, C3, C4 voltage, sir. I'm taking another set of the state variables. Total, it is 8 state variables. Here I'm leakage current and leakage is also, I'm taking a leakage current and secondary winding current also I'm taking as the 2 state variables. So that's why number of state variables is increasing, but we can briefly describe about the proposed topology. So this is the state space equation of the system can be written as follow: dx of dt by this is the state space equation. From the equation during the on state condition, A1 matrix and B1 matrix and C1 matrix will getting like this. And off condition, this is the matrix. From by using the A1, B1, and C1 and A2, B2, C2 matrix, we can get the state space average matrix of the proposed converter. A equal to A1 D plus A2. These all the this modeling is available in the Ericsson textbook, or G Ramanayan textbook also. These equations are available. The state space solution of that equation x equal to minus A inverse into B into Vg. By this equation, we can get the solution of the state variables. Okay. Here I'm getting the total 8 state variable solution also we're finding by using this equation. Here I'm verifying the large signal modeling. Suppose whatever model I'm deriving is right or wrong, we can verify by using the small perturbation. If the input voltage I'm varying from the step change in the input voltage 30 through 33 voltage, okay, by small, if they change the input voltage, how the pink color one is showing the simulation and black color one is showing the our large signal, our model. Okay, both variation is almost matching, similarly responding. That means our model and simulation are exactly matching. Then we are moving to large signal modeling. Once completed means then we'll go into the small signal modeling. In the small signal modeling, the small AC perturbations are considered to be about the steady state operating point. So once we are designing at that, suppose the duty ratio is 0.4, at input voltage is 30 voltage, output voltage is 360 voltage, and at out power is 250 watt. So these are the set of one operating point. For that particular operating point, we are adding the small perturbations in the input voltage as well as the duty cycle. Here you can show the your VG, the steady input voltage, we're adding the small perturbation. Similarly, in duty ratio also D, we're adding the small perturbation here. This one. So from this small perturbation, we can get the transfer functions. So the output to input transfer function V0 to VG, we're getting the at the time duty ratio perturbation is 0. D hat equals 0, and V0 by VG, we're getting this is the transfer function C into SA minus O into B. So this is the complete equation. So here the equation V M1 by N1, here M1 is the numerator and N1 is the denominator. This is the transfer function for the output to input transfer function. Similarly, we're getting the output to control transfer function B0 hat by D hat. Okay, B0 hat by D hat equation C into SA minus C whole inverse into A1 minus A2 of X. Okay. From this one also we're substituting that large signal modeling terms, we can get the numerator and transfer function. GVD is the control output to control transfer function. This output to control transfer function M2 is the numerator and N2 is the denominator. This one. So first of all, I'm drawing the open loop Borda plot. Okay, this is our proposed the transfer function. For the transfer function, I'm verifying the Borda plot in terms of theoretical, simulation, and experimental. Okay, the blue one is above the theoretical one, red one is the simulation one, and black one is the experimental one. So okay, we are getting the small deviation because of the we cannot consider the all the losses in the simulation and theoretically. Okay, so some factors are missing. That's why we are getting the small deviation, but almost exactly matching. Okay, so this is the Borda magnitude plot and phase plot. This is the open loop condition, output to control transfer function. Then we are going to the closed loop control. When we are going to the closed loop control, I'm adding the PI controller and one small lead compensator to increase the bandwidth of the converter. I'm adding the small lead compensator. This is our GC compensator. V0 by V reference equal to open loop transfer function into compensator by 1 minus GVD. This is the overall closed loop transfer function. For that closed loop transfer function, I'm finding this is the plot. Okay. For this plot, I'm getting the cutoff frequency almost to 600 is 600 is bandwidth of the converter. This bandwidth is comparatively very less. By properly choosing the compensator and lead compensator in better manner, we can improve the bandwidth of the converter further. If the bandwidth is less, means the rise time and everything is little bit slower. Okay, we can improve by adding the little bit better compensator. We can get the better cutoff frequency in this one. This is also theoretical simulation experimental. I'm showing the Bodeau plot of the converter. This is my experimental setup. In this experimental setup, laboratory prototype I'm above showing. This one, first one I'm implementing the analog controller. Next one DSP. This one is a wave vector controller. Here I'm showing this is the wave vector box. Okay. In that, this is the from this wave vector controller we can easily draw the Bodeau plot. Okay, we can easily this is the operating condition, 250 watt power, input voltage range, everything I'm showing. This is our wave vector window. Okay, these are wave vector software of corresponding VC. We can see the response, each and every sensor, whatever we're sensing, that will connect to the wave vector box. That wave vector box corresponding response will show in the wave vector window panel. Here I'm showing this is the D hat, D plus D hat. There's a small AC distribution I'm adding to the duty ratio. Okay. Similarly, the duty ratio corresponding output voltage also. V0 is output voltage on top of the small distribution we are getting here. Okay. From that one, we can draw the by using the THD window. By in the THD window, that particular frequency. Suppose I'm including the here 40 Hz frequency component. So that 40 Hz frequency component corresponding fundamental component magnitude also we can get from the by using that magnitude we can draw the Bodeau plot on the by using that fundamental component. Suppose I'm adding the 100 kHz component, 200, 300 different frequency components. That frequency component corresponding we can get the magnitudes. Okay, so by that one we can draw the experimental Bodeau plot easily by using the wave vector controller. Similarly, we can measure the bandwidth of the converter. Here, whatever bandwidth I'm getting the Bodeau plot, that is also similarly to the I'm calculating the bandwidth almost 55, 60 kilohertz and 720 kilohertz of the bandwidth. So it means bandwidth means the that's almost rise time, indicating the system rise time. And so this is the experimental. I'm calculating the bandwidth. So, but little bit this is a lesser bandwidth. Further, I want to try to improve this bandwidth also. This is the experimental waveform. ZVS turn on and ZVS turn off also achieving in this topology. The small signal modeling of the coupled inductor based higher order DC converter with leakage inductance effect is verified. They effectively recycle the coupled inductor leakage energy to the load by using active clamping technique. The ZVS operation of the active switch and output set diodes is achieved with low mutual inductance of the coupled inductor. These are the major features in this topology. At the time of when the fuel cell vehicles, these require two type of topologies. One is the bidirectional DC converter. Second one is the suppose if we are connecting the fuel cell case unidirectional high gain DC converters is required. Suppose in some cases also we require bidirectional DC converter. Suppose if I am placing the supercapacitor or any battery I am connecting, then the regenerative braking at the time the battery should be charged. At the time the motor will act like a generator. Whatever kinetic energy stored in the wheels that will transfer to the battery. So we need a high gain bidirectional DC converters also. In the present technologies, two types of topologies are using. One is the unidirectional power flow, second one is bidirectional power flow. In the proposed topologies, by changing the sum of the diodes with active switches. So you can see this one. These are the bidirectional power flow converters. Okay. Means a few of the diodes we can replace with the MOSFETs or switches. That converters also operate for the bidirectional power flow. Okay. That is suitable for the electrical vehicle applications. Final conclusions. In the proposed topologies, effectively recycling the coupled inductor leakage energy to the load using the active clamping and passive clamping technique. Okay. The proposed converter has the low conduction losses in the active switches because of its low semiconductor stresses compared to the similar topologies reported in the literature. And third one, the ZVS operation of the active switches and output side diodes is achieved with low mutual inductance in the coupled inductor. And third one, we are improving the reverse performance of the output side diodes. Okay, by using the leakage inductance current, we are reducing the current falling rate, and as well as the voltage stress appearing on the diodes also we are reducing. That's why the reverse recovery performance of the output side is improved. And with all bidirectional switches, the proposed topology can be applied to the electrical vehicle application as a replacement of the dual active bridge of the converter. These are the references. Thank you. Hello.
Sir.
Uh, okay, it's
Any
almost
question?
it's over. Any questions from the audience?
Participants can ask any questions.
Hello.
Sir.
I'm
Cannot
not getting any
respond.
voice. Okay, okay.
Which type of converters you have given, sir? Sir, in chat box.
Okay, your voice is not audible. One more time, repeat. Means what type of converts means here in the literature I'm showing all the possible high gain disease converters, but out of this coupled inductor based converters is very suitable for the LEV applications. Why? Because by using the lesser number of components, also we can achieving the higher voltage gain by coupling the one winding to another winding. And obviously, the number of components is very less. Means compared to study also showing that one the efficiency of this type of converters is very good than the other converters.
Sir, one more question, sir. From
Okay.
organizing team, what are the challenges of using high gain converters in electric vehicle charging systems?
Okay, ma'am.
Sir, am I audible?
Yes, madam.
What are the challenges of using high gain converters in electric vehicle charging
Okay.
systems?
Okay, madam. The first one, if you are placing the more number of capacitors in the electrical way, suppose if you are designing the any coupled inductor based converter, switched capacitor based high gain DC converter, if you are placing the more number of means more number of active capacitors means that the reliability of the converter active switches means capacitors is very less. Okay, so and interest currents of the capacitors also more, so there may be chance to damage if the we use the less number of the capacitors. Okay, and second one, our major aim is the reliability of the our electrical vehicle should be more. Okay, so when we are designing the converter at the time, minimize the number of the capacitors, and similarly the controlling the whatever I'm showing the bandwidth of the this high gain converters is major facing the problem with the bandwidth means instantaneously cannot respond. If you take the bandwidth is almost I'm showing the 600 and 700 Hz. It's required almost 3 kilohertz bandwidth is required for the better performance. So majorly you can by using the proper control techniques we can improve the little bit better bandwidth for the this proposed converters. This is also one more challenge.
Yes, sir. One more, sir.
Yes, madam.
How does core saturation of inductors affect high gain DC to DC converter efficiency?
Yes, madam. The major factor is the core saturation. If the once the core is saturated, it means if you are suddenly changing the power, if the vehicle, if you are increasing the rising means torque is required more. Suppose at the time of vehicle running condition, at the time we require a high starting torque means the high currents it is drawing from the motor. So if the current is drawing means correspondingly
Sir, mute la better, sir. Keep your mobile on mute.
Okay. Okay, now
Okay,
it's
sir.
audible.
Yeah, sir. Yeah, sir.
Okay.
Sir, one more
Okay.
question is there, sir.
Okay, madam.
May I know, sir, what are the different types of these converters used applications point of view? One, sir, one participant is asking, sir, in the chat box.
Okay. In the application point of view, I'm showing the different type of in the recent kind of vehicles. Two batteries, either two batteries are using, or one battery and one supercapacitor are using. The other one is the battery and another is the fuel cell is using. So based upon that application, the converters is changing. Okay. Suppose if you're using the supercapacitor, we require the bidirectional DC converters. Suppose if you're using the flywheel, or suppose you're using the fuel cell, at the time unidirectional converter is required. Okay. Based upon that application, different type of converter we can choose that nature. Suppose if I'm taking the fuel cell electrical vehicle, I'm choosing my topology is the exactly suitable for the electrical vehicles. Hello.
Okay, sir. Any questions from participants? You can ask directly.
Orange handprints.
Okay, sir. No more questions from audience.
Okay, ma'am. Thank you.
Okay, sir. Sir, I wanted to take a moment to express my heartfelt gratitude for your valuable contribution to our faculty development program.
Thank you.
Your insights and expertise truly enriched the experience for all participants. The topics you covered were not only informative, but also igniting new ideas and approaches in our teaching practices. Your ability to engage and connect with the audience made a significant impact and have received numerous positive feedback from attendees. Thank you, sir. Thank you once again for sharing your knowledge and for your dedication to fostering professional growth. We hope to collaborate with you in future programs, sir. Thank you, sir.
Ma'am.
Thank you for accepting our invitation.
Okay, ma'am.
Thank you once again, sir.
Okay.
Thank you, dear all participants. And tomorrow we'll meet at 1:45 with another topic. Thank you.
Okay.
Feedback link was shared in chat box, in YouTube link as well as in Zoom link. You can fill it. Thank you all.
Okay, ma'am. Okay, ma'am. I'm leaving now.
Yes, sir. You may leave.